Have you ever wondered why the COVID-19 Omicron variant is so contagious? Based on the most recent estimates, about 20 million Canadians have been infected with Omicron. Believe it or not, the reasoning behind its high transmissibility lies in the science of receptors. In order to better understand the high transmissibility of Omicron, we must first have a general understanding of how a drug molecule, also known as a ligand, interacts with the cell. To do this, we have to go a few decades back in history to the pharmacologist A.J. Clark. Clark was fascinated by how drug molecules bind to receptors to stimulate a response in the cell. So he proposed the Clark or occupancy model, which has 5 main ideas or principles. First, drugs create responses by occupying a receptor. The amount of response produced depends on the amount of drug molecules that are present. One drug molecule binds to one receptor. For maximal response, all receptors have to be occupied. And lastly, there are always more drug molecules than receptors. Understanding the Clark model is just the very first step. There are some additional properties of receptors that we must discuss. Let's say we have a receptor sitting on the membrane of a cell. Then a molecule makes its way to the membrane and occupies the receptor. At this point, some ligands may occupy the receptor longer than others. This property is known as affinity. Affinity is the ability of a molecule to bind to its receptor. You can think of it as the stickability of the molecule, or how attracted the molecule is to the receptor. The higher the affinity, the longer the molecule occupies the receptor and the bigger the response generated. The actual amount of response that is generated by the drug molecule is called efficacy, while the concentration or the amount of drug molecules needed to produce the different amounts of response is known as potency. We can get a better sense of these values by looking at them through a certain graph called the dose-response curve. On the x-axis, we have the concentration of the drug molecule that we have, while on the y-axis, we have the amount of response produced. Based on the empirical studies of different drugs, a dose-response graph takes this form of a curve. But how are potency and efficacy related to this graph? Well, the higher the response, the greater the efficacy, because more response is generated per unit of drug. On the other hand, the lower the concentration of the drug needed to stimulate that response, the more potent the drug is. Both of these factors depend on the affinity levels of the drug. At this point, you're probably asking yourself, how does this A.J. Clark guy, affinity, and dose response curves have to do with Omicron? Let's do an exercise. Pause this video and try to come up with an explanation of the high transmissibility of Omicron. The Omicron variant can bind to human angiotensin converting enzyme 2, or ACE2 in short, for a longer period of time. In other words, it has a very high affinity for the ACE2 receptors on the human respiratory tract, making it easier for the virus to infect the host, thus making it more contagious. It's interesting how such a small change in affinity can lead to such a huge change in outcomes for so many people. Additionally, some evidence suggests that Omicron's reduced lethality comes from this change in binding affinities. Affinity, efficacy, and potency are essential measures for all receptor interactions. For example, let's say you're assigned the task of finding an antiviral drug that binds to the spike proteins of SARS-CoV-2 variants. When you encounter a receptor problem in the wild, it's always important to ask these basic questions. How strongly does this drug bind to the target receptor? How much physiological response is produced upon drug receptor binding? And finally, what quantity of the drug is needed to achieve the desired level of physiological response?